So, good morning. After learning about intrinsic semiconductor, extrinsic N-type and P-type semiconductor, and how the formation of valency band, conduction band, and forbidden band takes place in a semiconductor, and based on the energy band diagram, we can differentiate metal, insulator, and semiconductor. Now we will, in today's lecture, we will derive the expression for electron and hole concentration in a semiconductor in equilibrium. I will first talk about few things which are required for derivation. The first one, in fact, I am talking about density of quantum states or density of electron states per unit volume, per unit energy range. In fact, I am simply informing you or giving you the idea about these density of states. They are the part of your solid state syllabus, and there you will come across the derivation of all these things. You have seen that in conduction band and the valency band, we will have to accommodate large number of electrons, and therefore there are several electron states, there are several energy states which are available. How are they distributed? That is given by the function density of quantum states or density of electron states, and the expression for the density of states per unit volume, per unit energy range is given by Ne is equal to 4 pi 2m to the power 3 by 2 upon h cube under root E. Here is the energy, m is the mass, h is the Planck constant, and Ne is basically the density of states per unit volume, per unit energy range. So if we want to, so this is the formula that you will come across in solid state physics paper in second paper, where considering a three-dimensional solid, you will come across the formula of density of states going as under root half. That means it's parabolic. If you take the square of any square is proportional to E, so it will correspond to a parabolic type of behavior. If we copy this formula to the density of electron states in conduction band, the formula gets slightly modified. In place of m, now we have Me star. Me star is nothing but the effective mass of electron in the conduction band. It is not 9.1 into 10 to the power minus 31 like of thing everywhere in the band. Depending upon the location of electron into the band, its mass is different. You will come across the idea of effective mass in BSc third year paper 2 on solid state physics. M star is h cross square upon d square E over dk square. E is the energy and k is the wave vector. So once you have the behavior of E versus k diagram, taking the second derivative, you can find out the information of effective mass. I will not go into the details. The other thing here is that in place of E, we have under root of E minus EC. Why E minus EC? Because conduction band starts from EC. The bottom of the conduction band corresponds to EC. So energy reference here is EC. In place of 0, we have EC. So therefore, density of allowed electron states in conduction band is 4 pi 2 Me star to the power 3 by 2 upon h cube into under root of E minus EC. Similarly, if we write down the same formula in a valency band, then in valency band, we have to replace M by Mh star. Mh star here is again the effective mass of electron or the hole, rather in valency band it is a hole. So effective mass of a hole in valency band, and in place of energy, we will have Eb minus E, because Eb corresponds to the top of the valency band. If we plot them based on our energy level diagram, so you can see here on the x-axis, we have density of states per unit volume per energy range. This is EC. EC is the bottom of the conduction band. Sorry, EC is the bottom of the conduction band, and EB is the top of the valency band. So in EB, it will go like this, and in EC, conduction band, the energy density, density of states will vary parabolic way like this. This is the first thing that we have to basically borrow or we have to understand for this course. The other is the idea of Fermi-Dirac distribution function. You are familiar with Maxwell-Boltzmann distribution function. You must have used it at several places in BSc Part 1 and Part 2. That probability of finding a system at energy E and the temperature T is given by e to the power minus E upon kT. That is the probability, because at many places we have to make use of the probability distribution. So that Maxwell-Boltzmann distribution function is basically the old distribution. In the first paper on relativity and statistical mechanics, you will be introduced about basically the new statistics, and new statistics means quantum statistics, that is based on the classification of particle on their spin. We can categorize the particle in two different ways based on their spin. We can have 0, 1, 2, 3, 4, 5 particles. They have integral multiple spin. We call them as Bose-Einstein. Bose particles are bosons. They obey Bose-Einstein statistics. The example is photon. Photon has zero spin, so that it is called a boson, and it follows Bose-Einstein statistics. Coming to the electron, you all know that electron has a spin to be equal to half. So half, 3 by 2, 5 by 2. If the spins are like this, then these particles follow Fermi-Dirac statistics. These particles are called fermions, and they follow a different type of a probability function, EFE. EFE is 1 upon 1 plus e to the power E minus EF upon kT. E here is the energy, T here is the temperature, similar to the Maxwell-Boltzmann distribution function. But here EF corresponds to what is called Fermi energy. Fermi energy is also a very important function in solid state physics as far as the solid is concerned. This will also be discussed in more detail in solid state physics, and the probability function more in statistical mechanics in BSc third year paper. So this is nothing but a probability function. It gives us the probability of finding an electron at energy E at temperature T. So it is the probability of occupancy of a label at energy E and temperature T. So it gives us the probability that if you have some energy label corresponding to the energy E, what is the probability of its occupancy by an electron is given by the function Fe. And EF is Fermi energy. I will talk about Fermi energy more after this. So suppose the temperature is 0 degree Kelvin. So if the temperature here is taken at 0 degree Kelvin, so let us concentrate on this expression. So T here is 0, and if E is less than EF, E is less than EF means this numerator of the exponent is a negative. So negative upon 0 is a minus infinity. So e to the power minus infinity is 1 upon e to the power of infinity. So it is 1 upon infinity. So this is equal to 0. And so therefore EFE is now equal to 1. And similarly, if E is greater than EF, that means energy is larger than the Fermi energy. The numerator here is positive. Positive upon 0 means positive infinity. E to the power of positive infinity is infinity. Infinity plus 1 is infinity. And 1 upon infinity is 0. So probability is 0. So if the temperature is 0 degree Kelvin, you can see this graph where Fe, the probability function, is plotted as a function of energy. Up to EF, the probability is 1. And beyond the EF, the probability is 0. What is meant by the probability is 1? That means all the labels are occupied by the electron. That is what is meant by the probability of finding the electron at energy E is 1, 100% probability. And if the probability is 0, means the labels are there but they are empty. So we can define Fermi energy is the energy of the highest filled electron in a material. That is one definition. It is the highest filled energy state or energy of the highest filled electron state in a material at T is equal to 0 degree Kelvin is called Fermi energy. The other we can say it is basically the energy level which differentiates the filled and the unfilled state. Up to Fermi level, all the labels are filled, and above Fermi level, the labels are completely empty. So the uppermost level which is filled by the electron is basically the Fermi energy. So that is how we can define the Fermi energy. Suppose now T is larger than 0. If T is greater than, it is not 0 degree Kelvin. So then we cannot define basically Fe like this. Then the only thing we can say that if E is equal to Ef, that means the energy corresponds to the Fermi energy, then the value of Fe comes out to be half. That means if the temperature is not 0 degree Kelvin, then corresponding to E is equal to Ef, the probability of finding the electron is just half. If we plot the density of function that I explained you just before than this, if you plot any as a function of E, it goes like this. So here also, if you make a demarcation for EF, so all these states up to EF are filled and these states are empty. So at non-zero temperature, we can say the probability of finding the electron is just 50%. So I again plot now Fe as a function of energy along with the previous one, just like rectangular behavior. This is for T is equal to 0 degree Kelvin. But now if you raise the temperature, you can see it crosses from 0.5, because when E is equal to EF, you can see here that when E is equal to EF, the probability of occupancy of a label by the electron is just 50%. So all at non-zero temperature, the probability here is 50%. But you will see here that as the temperature increases, the tail of the curve basically moves close to the Fermi level. So when you will go into the details of Fermi-Dirac statistics or quantum statistics followed by the electron, you will come across the fact that not all the electrons contribute to basically different conduction phenomena. In fact, the electrons which lies in the vicinity of Fermi level, they basically contribute. But here in this case, you have to simply remember what is density of states and what is Fermi-Dirac distribution function. Why are we going to talk about these things? That will be clear to you in the next transparency. So with this idea of density of states function and Fermi-Dirac statistics, which is obeyed by the electrons, and electrons are basically the major carriers, hole are also the electrons. We will now derive the equilibrium concentration of electron in the conduction band and then the equilibrium concentration of the holes in the valency band. So what we do now, we divide the energy space from EC to infinity into small strips, and we are taking a energy separation range lying between E and E plus DE, and here we assume that DE is much smaller than E, so we can write down our density function or density of states function over this region. So this range here is now DE. So the number of quantum states per unit volume now between the energy range E and E plus DE will be the density of states multiplied by now DE. Since it is per unit volume, so it is still per unit volume, so that is why we call it as density. So 4 pi upon h cube into 2me to the power 3 by 2, E minus EC to the power 3 by 2, DE will also come here. That is not written. Now the number of conduction electrons per unit volume. These are basically the states which are available. Now, what is the probability of occupancy of these states by an electron? So we all know electrons are the fermions. They obey Fermi-Dirac statistics. So we multiply it by the probability function, that these are the number of states which are available. This is the probability of occupancy of these states by the electron. So we multiply it by the probability function. So we get the number of electrons per unit volume lying in this range. And once we know the number of electrons per unit volume lying in this small range between E and E plus DE, then we can integrate it from EC to infinity to find out the total number of electron concentration per unit volume into the conduction band. So it's very simple. It is very simple. You must have derived maybe at BSc part 1 level also. So I will do the same thing. That number of conduction electron per unit volume is Ne. into D, and we multiply it by the probability function, that is Fe. Then electron density in the conduction band can be obtained by integrating this Dn between the limits Ec to infinity, because our conduction band starts from Ec and ends at infinity. So we are now going to put all those values here, and you can see that it is 4 pi into 2 me to the power 3 by 2 divided by h cube, and h cube, and then E minus Ec to the power of E minus Ec to the power of 3 by 2 into 1 upon 1 plus E minus Ef upon kT multiplied by dE. Now here we are going to simplify it. So for electron in the conduction band, you can see these steps. For electron in the conduction band, E is larger than Ec. We assume as if the energy that we are taking is far from the conduction band. So if E is larger than Ec, the Fermi level lies in the forbidden band. You will come to know more about the Fermi level. Where exactly does it lie in case of intrinsic semiconductor and extrinsic semiconductor in the next transparency. But here we assume that it lies in the forbidden band. So therefore, if E is larger than Ec, Ec minus Ef will be larger than kT. kT is nothing but the thermal energy. So if this is the case, if the energy is far from the bottom of the conduction band, then since the Fermi level is lying in the forbidden band, so E minus Ec is obviously larger than kT. So we can now simplify this Fe. It is now equal to, because this is larger, so exponential term will be larger than 1. So we throw away 1 as compared to this, and Fe becomes now e to the power minus E minus Ef upon kT. And we can write this Fe function as e to the power minus E minus Ef divided by kT into dE. Now we can easily solve this integration. Let us assume that E minus Ec upon kT is now eta. Eta is a variable, so we consider that as a variable, and that variable is so with that variable we can write this as e to the power of, if you introduce this, we can write 4 pi into 2 me star kT upon h cube to the power 3 by 2. Then integration 0 to infinity, eta to the power of half, e to the power of minus eta into dn. This integral is very common. In fact, we can you must have solved this integral while solving the gamma function. So 0 to infinity under root of x e to the power minus x dx is under root pi by 2. So you can directly make use of this integral here and write the electron density or equilibrium concentration of electron n to be equal to 2 into 2 pi me star kT upon h squared to the power of 3 by 2 e to the power minus Ec minus Ef upon kT. These terms before the exponential, we can club them together and write it as Nc. Nc is 2 into 2 pi me star kT upon h squared to the power of 3 by 2. And this is called effective density of states of function in the conduction band. If you understand the derivation of n on the similar footing, we can divide the energy range from Ec to minus infinity or minus infinity to Ev into small intervals, and we take an interval between E and E plus dE. You know what is the density of states function for the valency band, and that is 1 upon this valency band. So Ne into dE, Ne here will be equal to 4 pi 2 mh star to the power 3 by 2 divided by h cube into Ev minus E to the power of half. But here now, what is the state in the valency band? Hole will correspond to the vacancy of electron. If the probability of finding the electron at energy E is equal to Fe, the probability of not finding the electron corresponding to that energy at that particular level will be 1 minus Fe. And what is the vacancy of electron? Vacancy of electron corresponds to the hole. So the probability of finding a hole means electron deficiency is 1 minus Fe. So that is why this has been multiplied by the probability function 1 minus Fe, and then we multiply it by this, and we can find out by integrating it from this. It should be minus infinity. Here it should be minus infinity. Please make these small corrections, because I am also using this online platform of teaching you all for the first time. So these types of mistakes, I think you can take care of, and I will also mention those mistakes while discussing these things. So it's minus infinity to EB is the limit of integration. 1 minus Fe, you can do it this similar. So this is very simple. So this one will cancel out, and it is e to the power minus Ef upon kT. And if we divide the numerator and denominator by e to the power e minus Ef upon kT, so it becomes 1 upon 1 plus e to the power minus e minus Ef upon kT. Again, we assume that this energy E is at a closer distance from EB. Then we can again assume that the function here is simply larger than EF minus ES minus E is much larger than KT, and therefore this exponential term is larger, and we can ignore 1 in comparison to this. So do the same thing again here. Again assume eta dash, a new variable eta dash, to be equal to EB minus E, and by using the same gamma function, you can derive the expression for the equilibrium hole density P to be equal to 2 pi mh star At upon h squared to the power 3 by 2 e to the power minus EC minus EF minus EB upon KT. We can again write this term as NB, and NB is called effective density of states in the valency band. So this is how we can derive the expression for electron and hole concentration in thermal equilibrium in a semiconductor in conduction band and the valency band. Now we come back to the intrinsic semiconductor once again. We have discussed in the last lecture that in intrinsic semiconductor, the number of electrons are equal to the number of holes, because these are thermally generated carriers. These are electron hole pairs. So the number of electrons are equal to the number of holes, and we call them as Ni. I stands for intrinsic carrier concentration. So we know in an intrinsic semiconductor, N will be equal to Ni, that is Mc e to the power minus Ec minus Ef upon Kt, and P is also equal to Ni. It is equal to Nb into e to the power minus Ef over Eb, Ef over Eb. So now we multiply these two. N into P is now Ni square. You will come across a law called law of mass action. In a semiconductor, the product of electron concentration and the hole concentration is always constant, that is equal to Ni square. Here, if you multiply these two terms, Ni square comes out to be Nb into Mc into e to the power minus Ec minus Eb upon Kt. Ec minus Eb is basically the energy difference between the bottom of the conduction band and the top of a valency band, that is the band gap. So we can write this at minus Eg upon Kt. If you recall Nc and Nb also, then there is a factor of t to the power of 3 by 2 here and t to the power 3 by 2 here. So we can write this formula as Ni square to be equal to At cube. I have clubbed all those constants together. So it is At cube e to the power minus Eg upon Kt. So if the temperature is constant, then the intrinsic carrier concentration is constant in a semiconductor. It does not depend upon the Fermi level also, because Ef gets cancelled. So it is a constant, it is independent of Fermi level, but you have to remember it's a very strong function of temperature. And you will see later that this is the expression that Ni square is equal to Ni square is At cube e to the power minus Eg upon Kt. And if you take the square root of both sides, so Ni will depend upon t to the power 3 by 2 and e to the power minus Eg upon 2 Kt. So it depends upon the temperature in a very strong way. You will see at the lower temperature, t to the power 3 by 2 will not be the dominating factor. It is e to the power minus Eg upon 2 Kt will dominate. But the higher temperature, T to the power 3 by 2 will also dominate, and you will make use of this formula to find out the energy band gap in one of the experiment in your laboratory, and that is basically in your curriculum. Now we derive the position of Fermi level in an intrinsic semiconductor from the fact that electron and hole concentration is same in an intrinsic semiconductor. So I have put here the electron concentration and the hole concentration together. If you take the log of both sides, so this EFI, I stands for intrinsic semiconductor. It is EC plus EB divided by 2 plus 1 upon 2 into KT upon NB over NI. If you put the expression for NB over NI, it will come out to be the ratio of the effective mass of hole and the effective mass of an electron. And if we take a simple assumption that effective mass of electron and holes are the same, so this term now becomes 1 and the log of 1 is 0, and therefore EFI will be equal to EC plus EB divided by 2. So this gives us a very important result that in case of intrinsic semiconductor, Fermi level lies midway of the forbidden band. It's a very important result, and normally it is almost every year it's the part of your examination. So in intrinsic semiconductor, the Fermi level lies midway of the forbidden band. That means between the bottom of the conduction band and the top of a valency band. If you raise the temperatures or if you change the doping, in case of N-type semiconductor, in fact, if you change the doping, it basically moves towards the valency band. But in case of P-type, if you increase the doping, it basically moves towards the valency band. You can see here from this figure, in fact, I have written 10 to the power 12, 10 to the power 13, 10 to the power 14, 10 to the power 15, 16, 17, 18. This is how I am changing basically my acceptor concentration here, and then this is the curve. Similarly, I have not written the concentration here, but they correspond to the same value, 10 to the power 12, 13, 14, 15, 16, 17, 18 per centimeter cube, per cubic centimeter change in acceptor concentration for P-type and donor concentration for N-type. That is why you will come across that in case of N-type semiconductor, Fermi level lies close to basically the conduction band, while in case of P-type semiconductor, the Fermi level lies close to the valency band. Okay, in fact, later we will talk about that even if you increase the doping, then depending upon the nature of the semiconductor, whether it is degenerate semiconductor or non-degenerate, it will cross even the valency band and the conduction band also. But right now, this is the case of a non-degenerate semiconductor. So in non-degenerate semiconductor, Fermi level will lie close to the conduction band in N-type and close to the valency band in P-type. You can understand it very well based on the function Fe also, that more the electrons in the conduction band, it will shift towards the conduction band just to indicate that Fe is growing, Fe is increasing. Similarly, if it goes towards the valency band, that means the probability of finding the electron is less, more number of holes are there, so it goes down and it moves towards the valency band. So this is how the Fermi level changes as a function of donor concentration. Now, in fact, if you look at these figures, you see one more level, that is the donor level in case of N-type semiconductor and acceptor level in case of P-type semiconductor. So I will explain this also before I stop for this lecture. So here, if you look at this, in fact, the dense donor level lies just below the conduction band. Why just below the conduction band? Just below the ionization energy below the conduction band. The separation between the donor energy and the conduction band bottom is just the ionization energy of the donor. Similarly, here also, if we consider the acceptor level, it is just electron affinity difference above the valency band. So, in fact, if you just look at this energy level diagram, there are two ways to get the electrons to participate in the conduction game. In case of N-type semiconductor, either you excite an electron from the valency band to the conduction band, that is basically thermal generation or electron hole pair generation by helping an electron to switch over from or to take a transition from valency band to the conduction band. But we can do the same thing by adding impurity to it. Impurity just need a very small amount of energy. That is why the donor level lies below the conduction band, because it donates the electron, so that electron is available in the conduction band. Similarly, for p-type, very much less amount of energy equal to the electron affinity is needed to help an electron to move from valency band to the conduction band, because we have to have more number of vacancies in the valency band to have more number of electrons. So all those electrons take a transition to the acceptor level, giving rise to more and more number of holes in the valency band. So you have to understand basically this logic of valency band and the conduction band in a more better way to understand these semiconducting material and semiconductor devices.